So now we'll see question number 11 of the chapter Metallurgy. The question reads as, at 1100 degrees Celsius, which of the following reactions is thermodynamically most favorable? The options are A. TiO2 plus C giving Ti plus CO2. Option B is CO2 plus C giving twice CO. Option C, Al2O3 plus thrice C giving twice Al plus 3CO. And option D is Cr2O3 plus 3C giving 2Cr plus 3CO. We are also given the Ellingham diagram representing various oxidation reactions. So now we have to arrive at the solution using this Ellingham diagram. So let's get going with the solution.
Okay, so let's look at the first reaction. Okay, it's made up of two set of reactions, I'll say. The first one being TiO2 going to TiO, going to Ti.
Yes.
And the second one being, I'll write it down first, TiO2 going to Ti. The second one being C going to CO2. Okay, now if we look at the Ellingham diagram, we need to analyze the feasibility of this.
So actually we would add up the two reactions delta G and find a net delta G.
Exactly, that's what we are going to do.
That what decides the feasibility of the final reaction.
Exactly.
Okay. So now we would continue with option B. Now what does option B say?
Actually first we'll analyze TiO2 to Ti. So if we look at TiO2 to Ti, so at 1100 degrees Celsius, if we see it, we see that it is located somewhere here. Right, so whatever the value is negative, this much value is negative for Ti to TiO2. Correspondingly for TiO2 to Ti, that much value would be positive.
Correct.
Right, so this much value is positive. Okay, in case of that, the corresponding reaction that is happening is the other reaction. The second half of the reaction is C2CO. At 1100 degrees Celsius, what is the value of delta G for that is this much negative. Right.
Okay.
So this much difference will incorporate the. Okay, if we look into it, sorry, this much part was positive. Okay, actually the second part of the reaction I don't think was this thing. Second part of reaction is C2CO2. It is not C2CO.
Okay.
So we've analyzed it wrong. C2CO makes it much.
So basically the difference is that quite small one. The C2CO2 line is the straight horizontal line.
Yeah, exactly. And this much part, okay, was the difference is going to be very, very small. In fact, it's going to be this much positive only. The reaction will be highly infeasible.
Okay.
Now we move on to the second part. CO2 plus C gives you twice CO. We can write it down as CO2 going to CO and C going to CO. If you if you analyze the first reaction, that is CO2 going to CO, so we'll see we can judge it through this line, CO2 going to CO. So it will be if you look at 1100 degrees Celsius, this will be negative by this much amount. Right, I'll use a different color pen to point it out. This will be negative by this much amount.
So actually the reverse reaction is actually what is being asked.
Yeah, so this is positive by approximately this much amount, which is equal to this, and this is equal to this.
Correct.
Right, so now we look at the second part of it, which goes by C gives CO.
Okay.
So if we look at it, C going to CO at 1100 degrees Celsius is highly negative. So if you look at the difference, it's going to be huge. It's going to be highly feasible.
So the net sum would be very, very largely negative. Hence delta G is largely negative, which implies reaction is extremely feasible.
Okay, now we move to the third part of it, which goes like Al2O3 plus thrice C gives twice Al plus thrice CO. Okay, right. First we analyze the first part of it, which goes like Al2O3 to twice Al. Al2O3 to twice Al at 1100 degrees Celsius is located somewhere here. So if we look at it, this much delta G is negative for it. So the reverse reaction would have this much positive delta G.
Correct.
So the second part goes like thrice C to CO. Okay, if we analyze thrice C to CO or C to CO, I'll show you that it doesn't make a difference if it is thrice C to CO or
actually both are the same thing, because if we multiply delta G by the factor of 3, each of the terms get multiplied by a factor of 3, hence the slope will not change.
Exactly, that's what we are referring to. Okay, so C to CO. Now at 1100 degrees Celsius, we see it lies somewhere over here. Right, 1100 degrees Celsius, sorry, it lies somewhere over here.
Okay.
So this is this much negative. Right, so we analyze this much positive minus this much negative makes delta G positive. So hence this reaction is infeasible.
Okay.
Now we'll
analyze the option D.
Cr2O3 plus thrice C gives twice Cr plus thrice CO. Okay, now twice Cr plus thrice CO. Now if we look at this Cr2O3, okay, at 1100 degrees Celsius, this is going to be this much infeasible, this much negative, I'm sorry. So correspondingly the opposite reaction Cr2O3 to Cr would be this line this much positive. So what is the second part of the reaction that we are seeing? It is going to be C2CO. C2CO will be lying over here at this point of time, as you see. So the reaction is feasible, but if you compare with the difference that we obtained in B part, it is much less.
Like B part, the difference was extremely large. Here the difference is small compared to that.
So the answer is B.
B. So now we analyzed like Ellingham diagram for each and every reaction and finally concluded that CO2 plus C giving twice CO is thermodynamically most favorable reaction at 1100 degrees Celsius. So now we move on to the next question. Okay, so now we start with the question number 12 of chapter Metallurgy. The question reads as, which of the following statements is incorrect? The options are, option A, Si cannot reduce MgO at all. Option B, Al can reduce MgO above 1500 degrees Celsius. Option C, Al can reduce Cr2O3 as well as TiO2. And option D, Al cannot. Check the correction. It's Al cannot reduce ZrO2, but Mg can reduce ZrO2. So basically it's a simple application of the Ellingham diagram which is given in the figure, and hence we need to solve it using this.
Okay, so we were doing part A, so we think about it. We need the graph from Si to SiO2 and Mg to MgO. If we look at Si to SiO2, we'll see it lies over here, right? And so Mg to MgO. Where is Mg to MgO? The graph plots like this. So it says that Si to Si cannot reduce MgO at any point of time. This statement is not correct. Okay, as you'll see that here is a point of intersection where Si to SiO2 moves below Mg to MgO. So here is the temperature corresponding to this temperature. It can reduce this. So now we move to the option.
Actually, it's above that temperature, right?
Yeah, it's above that temperature. Did I say below?
No.
Okay, right, it's above the temperature. So Al can reduce MgO above 1500 degrees Celsius. So Al to Al2O3 let us analyze. So this is a graph. And Mg to MgO. So it goes like this. So you see till 1500 degrees Celsius what is happening? Al to Al2O3 is above this. So this reaction is not possible. Al cannot reduce Mg to MgO below 1500 degrees Celsius. Now once we move beyond 1500 degrees Celsius, this reaction is possible. So hence the statement is true. So this is not incorrect. Al can reduce Cr2O3 as well as TiO2. Okay, this is a general statement, so we need to find point of intersection at any temperature. Okay, if we find point of intersection at any temperature, this is possible. So can reduce Cr2O3 as well as TiO2. So we look at this. We have got Al to Al2O3. We can look here. Now Cr to Cr2O3. Is there any point which is the point of intersection? We see here. This is the graph. So it intersects at this point. In fact, we plotted the wrong one for Si to SiO2. It was here, but still we had the point of intersection. The one we plotted was for Cr to Cr2.
Okay.
So now Ti to TiO2, that is what we need to look for. Where is the graph for Ti to TiO2?
It's just below Si to SiO2.
Okay, right. It lies over here.
Huh.
So we see it also intersects, and at some point of time, in fact, below this temperature only, we can see Al to Al2O3 is below it.
Yes.
So exactly. So we don't need to look for point of intersection. In fact.
Correct.
So even at this temperature, we'll see that it can reduce it.
Okay.
So it says Al cannot reduce ZrO2. Now, which we'll look again at Al going to Al2O3 and Zr going to ZrO2. You'll see that the graphs are in parallel. So and Zr to ZrO2 is always lying below
Al to Al2O3.
Hence the reaction of Al reducing ZrO2 is not possible.
Correct.
And hence this statement is correct. Now we look at the second part of the statement, which goes like Mg can reduce ZrO2. Mg cannot reduce ZrO2. So
Mg can reduce ZrO2.
Oh, I'm sorry, Mg can reduce ZrO2.
So basically, as Mg is below ZrO2, Zr to ZrO2 line, so it will always reduce. It will reduce only below
1500 degrees Celsius. There is a temperature where it is intersecting.
Okay.
If this corresponds to 1500 degrees Celsius, this could be somewhere between 1105 and 1500.
Yes.
So here above this it will not reduce, below this it will. So as a result, this statement is also correct. The answer is hence A, and we move forward.
So now we start question number 13 of the chapter Metallurgy. The question is, Fe cannot be extracted commercially by thermite reduction process. So what is the reason basically for this is being asked in the question. The options are A. Very high temperature is associated. Option B. Fe is more electropositive than Al. Option C. Al has a very high affinity towards oxygen. And option D. It is very expensive. So now we get going with the solution.
Actually, I won't call it a solution in the first place, because this is where the mugging up portion comes. Mugging up nahi, I'll say it is a fact that Fe cannot be extracted commercially by thermite reduction process because it is very expensive. That is the fact, and that is why we use carbon reduction for it. So this is a fact you got to remember, the details of which you need not think about.
Okay, so it being very expensive, it's not exactly like an ore. Extraction is not commercially feasible, hence this process is not followed.